excited. I don't know about you, but we are coming towards the end of the semester, and now we get to start a cool topic, DiffyQ. So I have taught an entire course on DiffyQ, and we're only going to scratch the surface, literally scratch the surface. But I hope you're interested in this, and I hope this inspires you to take a full DiffyQ course. But we're going to start with a couple brief tools. First of all, what's a differential equation? We call it DiffyQ for short, or DQ. So let's get started. So first of all, some basic tools. Basics. What is a differential equation? Looks like Dairy Queen. Like I want an ice cream now. Okay. So a differential equation usually has like a y prime or a y double prime or higher order derivative in the equation. We're only going to start off, we're going to have a couple special cases, but we're going to mostly use a single derivative. So the most basic differential equation I can give you is literally y prime equals y. What do? Well, you look in your memory banks and you say, wait a second, I know that there's a function that is its own derivative, so I know that this function will solve this differential equation. Okay, so that's the solution to that differential equation, and I could put a constant out front of it. So the general answer to this question is that this is the solution to this differential equation. It's really that simple. Okay, so let's do another one. What about if we say, what function can I take the derivative of 4 times and I get back home to the original equation? Well, let me see. This works for sine of x minus sine of x, cosine of x, and minus cosine of x. And those are the 4 functions in the whole world that will do this for you. Okay? Great. Hope that was helpful. Moving right along, what about y prime? So when you take the derivative of something, you get the negative of the function back out. Well, this would be true for y equals e to the minus x, for example. When you take the derivative of e to the minus x, it kicks out a minus sign. And we usually do use this expression, it kicks out a whatever. So we'll say, if you have y equals sine of 3x, and you take 2 derivatives, it'll kick out a minus sign and a 9, for example. We use that kind of expression to indicate that after 2 derivatives, you're kind of back to where you came from, but you get a 3 comes out twice, and a negative comes out once. So we do use that expression, it kicks out a. It's very colloquial. You wouldn't use it in formal writing, but we use it all the time in discussing what it does. Okay, so there is something else, y equals y double prime. There are 2 functions that I want you to be aware of that do this. We call them hyperbolic sine and hyperbolic cosine, but we just say sinh and cosh just because it's easier. Okay, so sinh is e to the x minus e to the minus x all over 2, and cosh is e to the x plus e to the minus x all over 2. And if you take the derivative of sinh, obviously you're going to get back to cosh. So its derivative gets you back to cosh, and its derivative, well, do it for yourself. It'll take you back to sinh. So they toggle back and forth. And you may say, well, so what? Well, they're pretty cool, and they come up a lot. And something weird about sinh and cosh is a little memory trick. Sine of 0 is equal to sinh of 0, and cosine of 0 equals cosh of 0, which is 1. But those are the only places where this works. Everything else, like, it doesn't work. So don't try to generalize that. That's just to get you started, to remind you which is which, because I'm forever forgetting which one is sinh and which one is cosh. So that's how I remember them. Okay, so the first thing you do after you've been introduced to the idea of what is a differential equation, then that's just the briefest of all possible introductions. You need to know how to verify that something is a solution to a differential equation. So we usually just use the lazy word show. Show that y equals blah, blah, blah solves blah, blah, blah. This is the easy way to ask a student to verify a solution to a differential equation. So, for example, show that y equals sine of x solves y bing, 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 bing equals y. So the way you would do this as a student is you'd say y equals sine of x, and you would dutifully take some derivatives. And you'd say, oh my gosh, we got back, and so that proves that this worked. Okay, so that would be how you would verify these things. You don't usually have to take 4 derivatives, but you usually have to do something else that's equally annoying. Okay, so you already have been solving differential equations. If we say dy dx is some function of f, it could be like, let's use a polynomial. You've already been solving this kind of differential equation all year. So what you do is you just put the dx on the other side, and you stick some integral symbol around it, and then you say y equals x to the 8 over 8 plus x cubed. There we go. And then you always do the plus c, your constant of integration. Okay, so you've already been solving these differential equations all year. It's just now we're putting this into a broader context and saying, hey, that's technically a differential equation because we had a y prime right over here in the equation, and then you had to solve it. So you technically did solve a differential equation. But what if we do something a little more nuanced? What if we say something like x times dy dx equals 8y? And you can use this symbol y prime whenever you want, but sometimes it's more convenient to use the Leibniz approach, and sometimes it's better to use Newton, and it's just whatever's convenient for you. All right, so I'm going to pull a trick, and this is something called separation. Like, for example, you might just be able to figure out what this is, but let's say you couldn't really just figure out what that is. You want the dx to go on the other side, and so for you have x times dy equals 8y times dx. That's not really convenient for you. And so what we're going to do is we're going to let the x go over there and the y go over there, because that would be much more convenient. So the 8 can go wherever it wants. It doesn't matter. Dy over y is equal to 8 dx over x. Now we can integrate both sides. Well, what did we just do? We used a trick. This trick is called separation of variables. Anytime you have a situation where you can put all the y's on one side and all the x's on the other, and you can turn it into 2 different calculus problems, then you just do the 2 separate calculus problems and you don't worry about it, okay? So let's go ahead and solve this then. So I'm going to shoot this one off and say this is natural log of y plus some constant. And this is going to be 8 natural log of x plus some constant, but I don't need a constant on either side. Okay, it doesn't really matter which one you put it on. Okay, you could put 2 constants, but since it all washes out. So what do we have? We said natural log of y plus some constant equals 8 times natural log of x. If we're dealing with a strictly positive situation, we can just put the 8 up here if we wish, and we can Also do the following when you're multiplying. Natural log plus something is like multiplying the original function. Okay, so I'm going to actually just hide the constant in here for you. Think about why that makes sense. And now I can say like y is equal to, actually, you know what, I'm going to just put the plus c over here. And then I can, I'm going to end up multiplying it into the x to the 8th. It's because we ended up with natural logs on both sides, so the plus constant ends up as a times c. Let me just do that a little slower for you, because once you know that that's what happens, you'll just naturally do that. Okay, so what are we going to do? We're going to rewrite this as natural log of x to the 8th plus natural log of something else. I don't know what that natural log is of, so I put a tilde on top. And then that's going to be like natural log of c tilde x to the 8th. And again, let's just hope everything's positive for the moment. Now we can just say y is equal to c tilde x to the 8th. But since it's just a constant, I could be lazy and just say, wait a minute, this could have been the tilde in the first place. It could have been the other c. Okay, but the point is we kind of sometimes play fast and loose with c as long as there's only one c. If there's two different c's, then we have to keep track of it. But if there's only one constant of integration, we can just throw it around willy-nilly. And a lot of times we don't even bother to notate that the thing we just did changed the constant. So c equals natural log of c. Well, it isn't, but that's okay. It's just kind of a placeholder because there's extra freedom in the problem. Now, anyway, let's see if we are telling the truth anyway. So let's just get rid of all these calculations and see if this actually solves the original differential equation. But we can be asked the question something like, show that y is equal to 4x to the 8th solves, and then what was the original question? I said x, I'm going to use the other notation, y prime equals 8y. Okay, let's just go ahead and show that. Then we're going to have to take the derivative, equals 32x to the 7th, and so then we do the following. We say x times y prime is equal to 8y, so x times 32x to the 7th equals 8 times 32x to the 7th. I'm sorry. This y is this y. My eye slipped. There we go, right? 32x to the 8th equals 32x to the 8th. So now, once we have the right hand and the left hand equal, we successfully showed that that was true. Just as a little just in time, in case anyone's forgotten this, the derivative of natural log is 1 over x, but the integral of natural log, I don't think I even told you in this class, is a completely different creature altogether. It's really ridiculous, and if you needed to use it, you would just look it up on the internet. You could rederive it if you like, but anyway, don't confuse these two. Don't think that you can integrate natural log and get anything other than a big mess out the other side. Okay, but you can integrate 1 over x, and that's going to be natural log of x, and we should usually do the decency of giving it absolute value signs. But then hopefully the question will let you drop the absolute value signs. Another common trick in differential equations is to do something like this. Find the value or values of k so that such and such, y equals 3x squared plus k, equals, is a solution or solves, blah, 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 okay? And so the way you would go ahead and do this is you say like y prime is equal to 6x. In this case, the k disappears, but if the k were multiplied by, say, an x, you would have a plus k here. Okay, so whatever you do, you take some derivatives and you plug it back into whatever your equation is So it's all in terms of x. And then, and it has obviously a k in it. And so then you can figure these things out. You'll end up with an expression. So you might get typically a polynomial, but as long as it has the same structure, it doesn't even matter. You could have sine of x in it, provided you get something like, I'm just making something up here. As long as there's a way to make the right hand and left hand sides equal, and you say, aha, like as long as k equals 1, then we're good to go. So something like that. Or, you know, maybe the k isn't here. Maybe the k is like here, and then you'd say, well, k has to be 1. Or maybe there's nothing, maybe this is a k, and then it's like, oh wait, k has to be 3. Stuff like that. So the point is, you split your expression up so the right hand and left hand have the same basic structure, and then there's just coefficients in front, and you equate the coefficients so that everything works out. So that's how that works. I'm not going to give you more hints than that because I want you to work on number 4 yourself. And so you can go ahead and do that. And if you get stuck, let me know. But I think you should find it pretty straightforward. And finally, I want to take you through a little silly adventure that was inspired by your quiz, actually. So this isn't directly on the worksheet, but it's in the quiz. So if you have this guy, you've actually done this for a really, really long time, right? Y prime is equal to x, but you can actually solve it by separation. Maybe you didn't realize you could solve it, but now if I show you, you'll be sure to know how to solve it. So let me see. You're going to go x squared over 2 plus c. Let's make sure if you take the derivative, you get to x. Sure. In this case, c is 0. Actually, no, it doesn't matter. C doesn't have to be 0. My bad. Because in this case, there's no indication of what the constant of integration might be. It was lost by the time you got to the equation anyway. Okay, so you may say, okay, fine. That one becomes y equals x squared over 2 plus c. So how is the following thing different? What if I say dy dx equals y? Okay, now you could, well, first of all, you should recognize that's e to the x, or c times e to the x. You should know that. Because I just told you like a few seconds ago, and now I'm telling you again, because this is just really something that should be in your memory bank. But let's say for some reason you got confused and you said, okay, I'm going to solve it with separation, and then I'm going to get natural log of y equals x plus c, and then you're going to raise each side e to the power of natural log of y equals e to the power of x plus c, then you're going to get y. I'm going to drop the absolute value sign because hopefully, well, maybe I won't, I don't know, is equal to e to the x plus c, but I'm going to play fast and loose with the c. It's a different c now. Maybe I'll make it a capital C, and the other one was a lowercase c. And so there you go. So we got back to the answer we knew to be correct. But we didn't have to use natural log. And I also wanted you to see that there's some kind of structural similarity here. But it's the same but different. Okay, so this is a different thing. So yeah, they're both very, very simple. And then but this one, if you're asked, do you need natural logs to solve this? The answer is actually no. It's not necessarily the case. You can use natural logs as a waypoint to get here, but you don't end up with natural logs in the answer. And in fact, after you figure out what the answer is, you realize that the absolute value bars were not necessary because this part is not going to go negative anyway, right? Okay, and just because I want to kind of show you this little diversion, let's say dy dx equals 1 over x. I hesitate to do this, but I don't. Did you know you can actually flip this upside down? You could say take the reciprocal of both sides, and that's actually true. This is only true for the first derivative. First derivative is a special deal that dy dx is the reciprocal of dx dy. Only true for first derivative because it's actually a slope. It's the slope of a tangent line, right? But if you take the second derivative, it's actually not the same as the second derivative of the reciprocal. These are not the same. They're not, one is not the reciprocal of the other. It only works in the first derivative. And let me give you a numerical example of why this would be true. Okay, something really simple, just x squared. Okay, if you want to find the y, like what is the delta y here? You're just going to subtract consecutive values of y because you're going to do y2 minus y1 over x2 minus x1, right? And that's why I made the x steps equal to 1 to make this calculation very easy. All right, but what about if I want to take del squared of y? What I'm really doing is I'm treating this as y, and I'm still using x as x, okay? And that's how I get the second derivative. So then I'm just going to do something like this. I'm going to get change, 5 minus 3 divided by 3 minus 2. But since your denominator is going to be from that original relationship, then the idea of flipping your derivative only works on the first level because you're using y's and x's in kind of a symmetric way. One's upstairs, one's downstairs. But then when you take another derivative, you are referencing against your original x's. This is why when we say like d squared y over dx squared, what we mean is the dx is essentially getting used twice in the denominator. You're dividing by dx again, but the d squared means you're looking at the changes in y twice, but you're just dividing by x squared again. All right, so the role that x and y plays in the derivative is quite different. You can think of it also as a dependent and independent function, right? So this is the independent variable, and then y is the dependent variable. You could think of it as domain and range, dependent and independent, and if it's your statistician, you can think of one as a factor and one as a response. These words keep cropping up in mathematics over and over and over again, okay? But what it means is one thing changes more or less freely and the other thing changes in response to it. And when we look at that relationship at the first level, those two things are somehow balanced. And then when we try to look at the next level of change, that balance gets knocked off, okay? So this kind of flipping of the derivative only works for the first derivative. However, it still works for the first derivative, and that's the thing. People forget that you can pull this trick just for the first derivative. And so then you can do things like, well, what can you do? This looks like dy dx equals y, right? And we already know that the answer to this is y equals e to the x. Actually, y equals c e to the x. We know that that's the solution. And then you're like, but wait a minute, this has nothing to do with natural log. But yes, it does. Of course it does. Because we just flipped x and y. Okay, so we swapped x and y just so that we could solve this problem. Now let's swap it back again. So that means x equals c e to the y. So over here, this answer is x equals c e to the y. Great. So now we're going to take the natural log of both sides to get y, right? Because we're going to do, let me do that slower for you, natural log of c e to the y is equal to natural log of c plus natural log of e to the y. And then that is equal to natural log of c plus y. Okay, so right, so you still end up with y equals natural log of x plus a different c. And so we didn't lie to you. Like, you really can flip the derivative, but only for the first derivative. Do not try this trick with higher level derivatives. It only works for the first derivative. Special deal only for first derivative. Okay, so I looked back at your worksheet, and I have given you more than enough to fill your brains, and you should be able to get through worksheet 33. See you soon.